Okay, so having gone through the preliminary chapter, chapter 0, we are now ready to start chapter 1, limits and continuity. And in fact, this is where calculus really starts, and the notion of limits is in fact the thing that distinguishes calculus from the things we have seen so far, say algebra or trigonometry, these things. Now, based on the notion of limits, we of course have the other notions. One of them is continuity. These are notions related to functions. And then we have derivatives of functions and integrals of functions. But among these four things, although we start things with limits, but limits is in fact the most difficult to understand conceptually. So we will need examples to guide us, and which are in fact finally going to motivate the definition. So the authors say that we are first of all going to do it intuitively, and then we will look at the final formal mathematical definition, and then we will really understand why the definition is the way it is. It will look quite strange, involving some quantities epsilon, delta. So we will see why those things are needed and what in fact limit means. So these motivating examples we are going to use will in fact involve rates of change. Now rates of change is in fact something that we already know. Say we have a function, some function y equal to f of x. X is our independent variable, y is dependent variable. So unless our function is a constant function, in general what will happen when we change x, that is when we change the value of x, y will change. One can then ask, at what rate is y changing with respect to x? A rate of change. So we are going to first of all look at two rates of change in the examples that we are now going to see in the first section that we will start now. One of them is speed and the other one is population growth. So the authors have defined speed first of all, which is also something we already know, but it's important to see why we need speed here. So this is the first section. Rates of change and limits. Speed. The average speed of a moving body or moving object over any particular interval of time is the distance covered during this interval, distance covered by the body of course or the object, divided by the length of the interval. We all of us already know what average speed is. But there is a point that we should note here carefully. Say the body is moving and you observe its distance or its motion. You observe the motion of the body in this time interval, where at instant A you start your stopwatch or whatever you are using to measure time, and you stop it at instant B. Okay, some time has elapsed, and during this time interval the body moves from point A to point B along some path. Okay, we don't really know how the body is moving. We just know that during this time interval it has traveled some distance and it was at point A when the clock was at this instant, and now it's at point B. In fact, the body may have come to A from somewhere else, and after reaching B also it may continue its motion. We don't really bother about that. But the thing is that in this time interval also some things may have happened with the motion of the body, which we will not be interested in. The average speed of the moving object or body over this time interval is the distance covered during this interval, which of course in this case will be the length of this curve divided by the length of the time interval. So that what I was saying, that some things may have happened during the motion of the body which we are not taking into account in calculating the average speed. One of them may be the fact that the body may not have been moving uniformly during this time interval. It may have picked up some speed for some time. Within this time interval it may have slowed down. Okay, who knows? The only thing we are interested in is the total distance covered and of course the length of the time interval by which we are dividing. That is why this is average speed. It does not take into account what happens in between. It just takes the average of all those things. What things I am not saying particularly, but let me give you another example. Say you have a class of 5 students and you have conducted an exam, a math exam, and they have secured some marks. Okay, now those marks may be very different. Now if one calculates the average of those marks, then that average, that single number, in some sense represents all those marks roughly at once. Okay, that's what averages do. In spite of the fact that the average value itself may not be equal to any of the individual marks. Something like that is happening here. In some vague sense, we can understand that although here, instead of having discrete values like this, things are changing continuously. The speed may increase and then may come down. Ultimately, the body reaches B. We are not taking into account in these maybe infinitely intermediate things or values of the speed, whatever it may mean, but we are really interested in the average. Okay, but that's what average speed is. Let us now see the first example in which we have been asked to calculate the average speed of a body. Now this notion of average speed will give rise to a situation in which we will see that we are no longer able to do things with simple algebra. You can see that in this definition of average speed, we just need simply algebra, that's all. We are dividing the total distance by the length of the time interval, or the time it takes for the body to move from point A to B. That's just simply algebra, but that soon will not be enough. Anyway, so let's just see what example 1 is. A rock falls from the top of a 150 feet cliff. Okay, what is its average speed? A. There are two things we need to calculate during the first 2 seconds of the fall. And we also have part B. During the 1 second interval, okay, during the 1 second interval between the first second and the second second, that is between second 1 and second 2, fine. Now in order to answer this, we now need to know what actually happens in such a situation, that is, we need to know the physics. But instead of going too deep into the physics from which this can be answered, the authors have written like this: physical experiments show that a solid body dropped from a height to fall freely near the surface of the earth will fall by this distance y, which is 16 t square feet in the first t seconds of the fall. It's a fact that has been found experimentally. You already know what the things are behind all these things: acceleration due to gravity and such things. Okay, so now based on this, we can of course now calculate parts A and B. So what is it that we have to do? In part A, we have to find the average speed during the first 2 seconds of the fall. 1 second, 2 seconds. And then in part B, during the 1 second length of the interval, I mean the 1 second interval during second 1 and second 2. So these are the two things we need to calculate. So in part A, the average speed is delta y divided by delta t. Delta y is a change in the value of y. Delta t is a change in the value of t. In fact, delta t is that time interval that we are considering, and delta t is the length of the time interval. So the instant where your stopwatch stops and the instant where you started it's the length of the time interval. And during this time interval, the body has traveled a distance delta y, which is a difference in the y value, that is the distance value. So the interval in this case is this 0, 2, 0 second, 2 second. What happens at 2 second? The body has fallen this much, 16 t square, 16 times 2 square. And when the body was just being dropped, where no time in fact has elapsed, the body has fallen this much. That means it has not fallen, has not in fact started falling. And the length of the time interval is this. So this is just 32 feet per second. And in part B, the average speed is, so this is the second, that means the second interval, second 1 second length interval that arises in this situation. So this is 16 times 2 squared minus 16 times 1 squared divided by 2 minus 1, which turns out to be equal to, because 2 minus 1, 16 times 4 minus 1, that means 3, so 48 feet per second. Fine, it's just simply a computation. Now there arises a problem if one instead asks this: what is the speed of the rock at the instant 1 second after its release? Then we can just draw a simple diagram for the situation. This is our 150 feet cliff, that is the top of it, and the body was just released when the clock was started, that means 0 second. Okay, so the body is just here, it has just started falling. When the clock reached 1 second it has fallen by some distance, and when the clock reached 2 seconds, then it has fallen by some more distance, which is naturally, you already know from experience or from theory, from physics, that it will fall in fact more, because it will have picked up speed by then due to acceleration, due to gravity. Okay, so the first average speed that we calculated is in this interval, in this 2-second length interval, and the second average speed we calculated is in this interval. But here, however, we are being asked to calculate the speed at the instant 1 second, at that time instant after the release of the body. What shall we do to calculate this? Because you see, unlike these two cases, the 1 second instant is not a time interval, but rather it's an instant, a point of time. Okay, so do we divide something by the length of that? If you want, you can also regard this as an interval of length 0. Do we divide some distance by 0? Of course not, that's not allowed. So what do we do? How to calculate this? But you soon realize that even before calculating, you need to know what this in fact even means. Speed at some particular instant of time. What does it even mean? What is the definition of this notion? And you run into a problem, because here you are unable to divide by the length of length of an interval which has positive length. But you then start to think of what you can do, and eventually people realized that okay, we have the notion of average speed. And you see, the definition of average speed is not just simply something we made. Of course we have made up the definition, but it's natural. It is measuring on an average what happens to the distance when this much time has elapsed. But if we just simply look at a single instant of time, there you freeze the frame. If you are just, you say you have filmed the fall of the body, you freeze the frame and then ask what is the speed at this instant. It is just frozen. So that's why what we will do is this. We will in fact again calculate average speed, but not one average speed, but many average speeds in different intervals, where say, and this can also be done in several ways. We will see all these things in some interval that contains the 1 second mark. Say you take one such interval in which the 1 second mark is one boundary end, okay, and the other boundary end is say some other time which is a little more than 1 second, say 1.3 second. In this interval, of course, you can calculate your ordinary average speed. Fine, you get some value, say t1. What you then do, you make the interval smaller. In what sense? In the sense that you consider the other boundary. You keep this 1 second as one boundary. You consider the other boundary in such a way that it moves closer to this boundary. That means the interval is shrinking. Then here also you can calculate an average speed, say that value is c2. And do you realize why we are doing this? Of course, because we have been asked to somehow, even before calculating, now the situation has come down to defining the notion of speed at an instant. So somehow we are trying to divide by 0, but we cannot actually literally divide by 0. So we are dividing by smaller and smaller lengths of this smaller and smaller time intervals, and then we are seeing what happens to these average speeds. Another smaller one you take, you will get another average speed c1, c2, c3. If it happens that you come across a real number, whatever it is, such that these values are somehow themselves becoming nearer and nearer to c. If such a c can be found, then this c will be defined as the speed of our rock at the instant 1 second. And see, all of these things are really vague. Why? Because nearer and nearer to c, how near? In order to make these things precise, we need the actual mathematical definition of limits, which we will see. Okay, it will come. But before that, we need to go through the examples, and we will see that by the time we reach the actual definition of limit, by that time we will have become quite well versed, quite acquainted with this type of thinking. We will then, in the actual definition of limit, try to pin down these things that we have said, which are somewhat still vague. Okay. Now, this is in fact what we are going to see in the next example, example 2, which I will not do today. Instead, let us just see what the authors have said a little about free fall. That's because in this solution to example 1, they have mentioned this 16t square, right? So they have said something about free fall. So this is what the authors have said. Near the surface of the earth, all bodies fall. And also, why near the surface of the earth? This is probably something you already know from your physics lessons, but still, near the surface of the earth, all bodies fall with the same constant acceleration. The distance a body falls after it is released from rest is a constant multiple of the square of the time elapsed. Okay, so that's why 16t square. At least that is what happens when the body falls in vacuum, okay, where there is no air or some other such stuff, no gas, where there is no air to slow it down. Because you know that when you are releasing something in ordinary situations, if it's heavy, then it does not feel like it is being impeded. I mean, it is being resisted. It just simply falls. If it's somewhat heavy and solid and compact like this, well, I should not perhaps say compact, but something like this. But if it is quite light, say a feather or some quite light, say snowflake, something like that, then if a gust of wind comes, its fall is easily affected. So unless the wind is extremely strong, for example, the fall of this marker will not be affected. So that's what they say. At least that's what happens when the body falls in vacuum where there is no air to slow it down. The square of time rule also holds for dense, heavy objects like rocks, ball bearings, normal objects, and steel tools in the first few seconds of their fall, even through air. In the first few seconds, when you are releasing the body, when it starts to fall, I mean, it has of course picked up speed, it's heavy, so just when it starts to fall, it does not pick up that much speed. I mean, in the first few seconds or say few deciseconds or milliseconds, something like that. During that time, then because its speed is not great, the air resistance does not affect the motion that much. So during that time, the square of time law still holds for this kind of objects, even in the presence of air. Yeah, that's before its velocity builds up to where air resistance begins to matter. When air resistance is absent or insignificant and the only force acting on the falling body is the force of gravity, when that happens, we call the way the body falls free fall. Okay, when there is no other type of influence, no other force, in the absence of air, that is in vacuum, when the body is falling only under the influence of gravity, then it is free fall. But does the mass of the body not affect this acceleration? Actually, it does not affect. In the absence of air, I mean, if we are not considering other complexities, it is something like this, no? Say this is the earth, and you are releasing the body from this distance. Of course, in this diagram, compared to the radius of the earth or the diameter of the earth, this height is extremely high. But you should understand that I have just simply drawn it this way so that we can see things. The earth is so large that even if you go quite high, its curvature really cannot be seen or cannot be understood. So it is really that large. So what I am trying to say here is that near the surface of the earth means that the height from which we are releasing the body is insignificant compared to the radius or the diameter of the earth. Okay. But anyway, so this height is say h, and this is the radius of the earth r. Right? So you have your ordinary force of gravitation downwards, radially downwards, or radially towards the center. So if the mass of the object is m, then what is the force? The force of gravity will be equal to g, and because we are trying to calculate the force, we will need the mass of the earth also, so that is capital M. Now, so what will you write here? We already know the formula, divided by the square of the distance. This is really the force of gravity acting on the body or the object that has been released, or in fact, even if it is just simply kept here on something, this is the force that will be acting on it. But we also know that force is mass times acceleration if the mass is not changing. So in normal for such solid object, the mass does not change. So okay, so you can cancel out m from both sides. So you then get a sort of formula for the acceleration that will be resulting from the force of gravity. Note that this final relation is, in this relation you don't see the mass of the object. So irrespective of what the mass of the object is, the acceleration seems to be constant. Okay. And one more thing, if we take into account the fact that h is extremely small compared to r, then h plus r is as good as r itself. Okay, so this is our acceleration due to gravity, but provided we are considering the fact that we are looking at a perfect sphere, which the earth is not, where it has uniform density throughout, so that the force of gravitation is uniform throughout. No, that is not the case. It bulges a little at the equator, plus due to its rotation, and in fact that's why it bulges, there is centrifugal force which will reduce the gravity a little bit. Also, due to the irregularity of the distribution of matter, actually if one calculates these things, one will get slightly different values across the globe, but some rough or average value has been considered as the actual value of your g. In fact, this is your g, the acceleration due to gravity. Okay, so I'm just simply saying this because it's related to this free fall. So the point here is that if our object is being released in vacuum or not from a very high point, then during the first few seconds of its fall, if it is falling only under the influence of gravity, then it is called free fall. In that sense, the authors have used the word falling freely near the surface of earth. If you go really quite high, so that h is no longer so small compared to r, then of course this approximation will become very bad. In that case, this will really not be a constant anymore, but it will really start to depend on h. So that's why we say near the surface of the earth in this sense. Okay, so in the next, so I am ending things here itself. In the next calculus update, we are going to see how this can be handled, and in fact what is it that it even means to say this kind of thing, speed of the rock at that instant of time. Okay, and that will give rise to the notion of limits and the other things. In fact, because we are looking at rates of change and not just simply change, so actually we are looking at the notion of derivative towards which we will go. We will investigate these things in the next chapter, and then we will see where it goes from there. So that's just it. And tomorrow, I forgot last Saturday what is it that actually we did. Did we I think we solved Lee's exercise problems. If that's the case, then we will do Gallian, but if it is Gallian, then we will do Lee. So that's just it. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.